So what did we do last time? We spoke about how we have showed that entropy, which is ds, is equal to delta Q reversible by temperature, is exact differential. In other words, S, which is the integral of this thing, you go along a path reversibly, and every path will have its own heat that you add to the system. Even if it's a reversible process, it will depend on the path. That is a state function. So let's look once again at all the state functions we have seen so far. Where did we start with? Which was the first one? U. Followed by U, we had enthalpy H. And then entropy S. These are the three ones we have really looked at. In parallel, we have looked at state variables, which are pressure, variable, volume, temperature, number. The distinction between function and variable is a bit vague. You could very well think of these also as state functions. There is nothing wrong with it. And the path functions we have seen so far are Q and W. And as a corollary to this, we also saw that heat capacity can be calculated. Heat capacity at constant pressure and heat capacity at constant volume can be calculated from state functions, even though strictly speaking, heat capacity is capacity of Q, which is a path function, right? Even then it can be calculated from a state function. So this is where we have reached so far. We spoke about first law of thermodynamics, which said du is equal to delta Q plus delta W. The sum of two path functions is a state function. And we spoke about second law of thermodynamics, where we had three statements and we showed that all three are equivalent. So today we are going to talk in a bit more detail about irreversible processes. And through this, we are going to look at something called Clausius inequality. So we have talked about reversible processes. We have once in a while talked about irreversible processes, but we haven't really looked at it in detail. So look at it in just a little bit detail. And here I want you to recall of something that we did the first time we really spoke about irreversible and reversible processes was when we were, anyone remembers when we spoke and we calculated something for reversible and irreversible, and we showed one of them is always bigger. Which one? Work done, right? It was when we were expanding a gas from a pressure from a certain point initial to a certain point final. And we said that if we go reversibly, reversible means following equation of state, everything is well behaved. If you follow the equation of state, the work that we can get out of this process is going to be this red area. And then we showed that if instead we just slam the gas tight to the final, well, in this case, expanded the gas all of a sudden to the final pressure, then the work done by the gas as it expands is going to be the black one, right? So we showed that in this case, now let's also go back to our first law of thermodynamics and let's refresh our memories or like turn our mental gears at 9 a.m. Work done in this, when we define work done, we defined it as the work done by the system, right? Remember that sign convention? So in this case, dW is going to be negative or positive as the gas is expanding from VI to VF. Work done by the system, will it be negative or positive? Negative, why? No, the system is doing work. Go ahead. Yeah, the system is doing work as you are expanding. You know, as a gas expands, you can get something out of it. To contract something, you have to do work on it. So this will be, dW will be negative. So if I want to write down the work done in the reversible process, I can definitely write down that, or actually, let's use the delta symbol just to be consistent. I can definitely say that delta W reversible modulus is more than delta W irreversible modulus, right? Because this one reversible is the red area while the irreversible one is the black area. Right? But let's get rid of the modulus. If I want to get rid of the modulus, how should I write this equation? Go ahead. Huh? I could square root sides, but I don't know square things. That's what I'm going to do with square of what? Let's use a minus sign. It will have to be minus delta W reversible is more than minus delta W irreversible. Why? Because delta W reversible is negative. We just showed, right? We just mentioned that delta W reversible is negative because the gas is expanding. If something is negative, its absolute sign is equal to the negative of that thing, right? Is that clear? This is kind of subtle, especially for 9 a.m. So regarding midterm problem 2, 3, and 4, if you have problem with your grades, first of all, look at the solutions before contacting us. Okay, we will post them today. Look at the solutions. Problem 2, 3, and 4. If you have problem 2 onwards, if you have difficulty, contact Connor. Problem 1, if you have difficulty, send me a DM, direct message on Slack or an email. But first look at the solution. Okay, so keep this in mind. This is the first time we really saw about reversible and irreversible, but now we are going to make it a bit systematic. In order to make it systematic, let's consider system. So now, in order to make it systematic, we will talk about something called Clausius inequality, where we have a system in a state A, and the same system can be in some state B. Okay, this could be in pressure volume space, in pressure temperature space. I'm not going to draw coordinates. You have a system in state A, and you are changing it to state B. And let's say you're doing it through 2 different paths. One of them is a reversible path. I will call it R. And the other one is an irreversible path. I will call it I. Okay. Let's write down our first law of thermodynamics for both paths. We can write down du is equal to delta Q plus delta W. This is true for both path I and R, correct? This is just the first law of thermodynamics. True for I or R. It's true for both I or R, I and R, whatever you want to call it. What can we write down special for the reversible path? We now know certain things are true for the reversible path. One of them is that this delta Q is same as TdS for a reversible path. Remember, how did I do this? Because ds is defined as delta Q reversible by temperature. Right. So actually, before I go into TdS, sorry about that, let me just write it this way. So we can write it down as delta Q reversible plus delta W reversible. This is true only for R. And then we can use ds is equal to delta Q reversible by T. Therefore, du is equal to TdS plus delta W reversible. That's equation 1. Equation 2. Both apply to the system changing from A to B. Equation 1 applies to either I or R. Equation 2 applies only to R. My question for you is, what about du? Is du going to be different depending on I or R? No, right? Marco is very confident. Why, Marco? It's a state function. So what does that allow us to do? That allows us to equate the right-hand side of equation 1 with right-hand side of equation 2, right? Because du is same. Du does not depend on I or R. It's a state function. Therefore, delta Q, and I'm going to call it, instead of saying I or R, I will call it actual, right? An actual process, which could very well be reversible or reversible. We don't know what's happening. So let's call it delta Q actual plus delta W actual. So for what is this actual? This actual just means a shortcut for It could be either I or R, okay? One of either of these. Delta Q actual plus delta W actual is equal to TDS plus delta W reversible. Everyone happy with this relation? Okay, you guys are easy to please then. So let's look at this. Let's manipulate this equation. Therefore, TDS is equal to delta Q actual plus delta W actual minus delta W reversible, or DS is equal to delta Q. And I'm going to get rid of even the actual now and just call it delta Q for a general process where we don't know whether it's reversible or irreversible. Okay. DS is equal to delta Q by T plus delta 1 by T delta W minus delta W reversible. Okay, this is just a bit of manipulation, but we have written kind of an interesting equation. The interesting thing about this equation is when we saw the definition of entropy, our DS was delta Q reversible by temperature, right? Now we don't have that. This delta Q could be an irreversible process. This could be anything, reversible, irreversible, any path, doesn't matter. So contrast with DS is equal to delta Q reversible by T. It almost looks like that, but it's general. And in order to have this generality, you have some difference of words on the right-hand side. Let's call it equation 3. And let's go to next page. I will write down equation 3 once again. So we have DS is equal to delta Q by temperature plus 1 by T delta W minus delta W reversible. Okay, what can we do with this? So the example that I just drew over here, where energy work is being done by the system. Let's keep this example in mind where the work done was negative because it is what you are actually getting something out of the system. So when work is done by system, we know that delta W reversible modulus sign is going to be more than delta W, more than equal to delta W in general. Is everyone happy with this relation? This is just that thing that we wrote geometrically, we showed geometrically over there that, let me draw it over here. We had gas expanding from here to here reversibly, and then we had the gas expanding from same pressure we just slapped, but we just expanded all of a sudden to this pressure. The reversible work was this shaded area, while the irreversible work was this hatched area, right? That's the idea. And they are both negative. That's what I'm talking about here. So they are both negative. So I can do the same thing that I did over there and write it down as minus delta W reversible is, this is equation 3, more than equal to minus delta W. Okay. Cool. So let's manipulate this. This means delta W minus delta W reversible is more than equal to 0, right? 4. Let's put 4 in 3, and then we get the main inequality that's of interest to us today. When we put 4 in 3, what do we get? DS is equal to delta Q by T. And what can we say about this thing now? Is it positive or negative or 0? Huh? It's more than equal to 0, right? That's what we showed over here. Temperature cannot be negative. So it's got, we are working in absolute kelvins, absolute temperature. So this is positive. This plus something more than equal to 0. Therefore, DS is more than equal to delta Q by T. And this is equivalent to the second law of thermodynamics. And this is called Clausius inequality. Go ahead.
For your inequality, right below the absolute values,
Uh-huh.
one of the negatives not strictly true, because if it has a greater magnitude, then the negative value would be lower than the corresponding value.
But delta W reversible is negative. So I'm saying modulus of -8 is more than equal to modulus of -7.
Right, -8 is less than. Right.
Yes, but what I have written over here is not -8. What I have written over here is -8. I told you it's a bit of a trip for 9 a.m. It's confusing, which is minus of minus, okay? Keep that in mind that delta W, this thing itself is negative, okay? When I did this thing, I'm not saying delta W reversible is a positive thing. That is a negative thing, and I'm multiplying it with a minus sign. So this inequality is super, super, super important. Why is it super important? First of all, this S over here is S of system. This Q over here is heat given to system. So Andrew, right? Andrew, when he told us about his statement of second law of thermodynamics, what was your statement, Andrew? Pop quiz. Come on, man, it's your statement. Be more emphatic. I'm going to give it to someone else, man. You got to be more enthusiastic about it. It's okay. Andrew's statement. Anyone else remembers Andrew's statement exactly? It was even simpler. It was saying that the entropy of the universe, entropy of an isolated system, must increase during a spontaneous process, right? Must increase during a spontaneous process. So that was what was the problem with that equation? It was talking about the entropy of the universe. Now you're doing a chemical reaction. You want to study something practical, and you want to calculate, apply second law of thermodynamics to it. You can't just look at the system. You have to go and calculate entropy of the whole damn universe. That's going to be a bit messy. This equation is how really powerful, because all of a sudden it's not talking about entropy of the universe. It's talking about entropy of the system. So you can just focus on the reaction that is going on. You don't have to go and worry about everything else. Does this equation reduce to Andrew's statement? Is it equivalent? Why, Daniel?
Because we took S of the system and we set the system as the whole universe, but that must increase relative to.
Yeah, so if the system was the whole universe, then what is the Q for whole universe? 0, right? So this is equivalent to saying that ds isolated system is the same as universe, is more than equal to 0 for no, let me not write down for a spontaneous process. Strictly, I should not put equal sign is okay. Equal sign means that basically the reverse is also spontaneous, right? B going to A is also spontaneous. ds isolated system more than equal to 0 for spontaneous process. So it's equivalent to this, but this one is very useful. And all the free energies in thermodynamics, all the notions of chemical equilibria and all those things are nothing but a restatement of Clausius inequality. Law of mass action is nothing but Clausius inequality. Everything we do here on is basically going to fall out of Clausius inequality. It won't make your life easy. Starting next week, you will be deep in the land of partial derivatives. Okay, so it's again, I'm warning you to go and brush up partial derivatives. Starting next week, we will be doing something called Maxwell relations, and then the partial derivatives like explode. It's a lot. I mean, I used to hate it when I was an undergrad. I will be honest. It takes time to get warmed up with it. Okay, Maxwell relations are messy. You will find tricks to remember them, but if you pay attention from now on, you won't need the tricks. So next week, a lot of partial derivatives are coming. Okay, you have been warned. Any questions about this? So what is Clausius inequality telling us? Clausius inequality is telling us that if I have some system, this is clearly not an isolated system, right? And if I'm giving some heat to it, Q, the entropy change of this system must be more than equal to dq by t, right? If this was an isolated system, if it's a reversible process, then ds becomes equal to dq reversible by t, right? But now this generalizes it and tells you that if you don't have a reversible process, ds is actually more than equal to delta q by t. So this form of second law of thermodynamics has existed since the time of Clausius. It's in the form of an inequality. It's not an equality, right? It's an inequality. And for 200 years, it has existed as an inequality until 1998. Go ahead.
I have a question about the PV diagram on the board.
Yeah.
Why is it the case that there's no irreversible process that goes above the curve?
Oh, you could make one.
But
There is no shortage of irreversible processes.
So my question is, if that were the case, wouldn't delta W for that be greater than?
Nope. You won't be able to do that. You will, if you went above, then you have to come down somewhere and you have to do your bookkeeping. You have to look at the network, right?
Yeah,
So you are saying if I went from here to here,
yeah. and I went
then
down.
did this.
Yeah. Because for that delta W would be bigger, because the angle is bigger.
Good. So your point is that there is no expansion work, so I can simply ignore this. This is a good point. Let me think about that. But yeah, I think the most likely answer is going to be that there is not just expansion work, there is something else going on. But second law of thermodynamics, which says that irreversible work is always the irreversible work that you can get out of a system. Yeah, I will come back to it in a moment. Is always less than the reversible work that you can get out of the system. Also applies to the other direction. If you have a protein and you want to fold it, right? You have a protein existing as a long chain of amino acids. And if you want to fold it, in order to fold it, you have to do some work, right? If you fold it reversibly versus if you fold it irreversibly, you will have to do less work when you fold it reversibly, right? So this applies both ways. When you're getting work out of a system, it applies this way. When you're getting work, doing work on a system, in order to drive the system from A to B, you have to do more work if you're doing it irreversibly. If you're doing it reversibly, you can get it done with less work. What was your question?
I think I actually
Go ahead.
it wouldn't be isothermal. So you have to, so your temperature variable would change, which would make processes that involve really difficult because it assumes it doesn't assume constant temperature.
No, but his point is simpler. He's just saying if I look at the area under the curve, that looks more, and that could be an isolated process.
Yeah, so the temperature and the processes that involve changes.
But he's not asking about Clausius inequality,
Oh,
right? He's just asking about this equation, right? That's
Yeah.
you're Naveen, right?
Yeah.
So Naveen is asking about this equation. That has nothing to do with Clausius. So if anyone finds an answer before me, please post it on Slack and have it. Yeah, you have an answer? You have a question? Temperature is always positive. We are working not in Fahrenheit, we are working in Kelvin. If temperature was negative, our life would be in trouble. There is a reason why temperature is positive. That you bring up a good point. This is since, what's your name? Shechin. Oh yeah, you were the only student who came to my office hour the other day. I'm so happy. Thank you, Shechin. It's so lonely on the Zoom during my office hour. So why should the temperature actually always be positive? Why can't we have negative temperature in the Kelvin scale? Why don't we ever talk about -5 Kelvin? Go ahead.
It's a measure of kinetic energy, which is positive.
That's one way of looking at it, but thermodynamically, go ahead.
it's because at 0 Kelvin, atoms stop moving completely. Electrons, which can't happen because of area.
Okay, I want you all to go and Google negative temperature, and you'll find that there are actually temperatures which are negative in Kelvin. The funny thing is, negative Kelvin, what? Yeah, but you know the funny thing? Negative Kelvin is hotter than 0 Kelvin. I'm not kidding. Negative temperature exists in systems. So the most important thing about thermodynamics is it does not apply to systems with 1 or 2 particles. It applies to systems with infinite number of particles, right? as soon as you go to systems with 5 particles or 10 particles, he found it. Did you find it on internet?
Well, I'm just reading a Wikipedia article.
It's cool, it exists. And the funny thing is, it's hotter than, it's hotter than 0 Kelvin. And if you take graduate thermodynamics, you will study that the most important reason why temperature is always positive is because this partial derivative, delta S by delta U at NV is positive. However, in spite of this is all true when in the thermodynamic limit. So the most important assumption we are making in all of this semester is we are not really talking about 1 molecule or 2 molecules. We are talking about Avogadro number is large for a reason, like 10 to the power 23. We're talking about huge number of things. So that negative temperature happens in system where n is actually very small. Systems with 10 electrons or 20 atoms. And I think on campus we have labs where people have negative temperature systems, which are actually hotter than 0 Kelvin. This is crazy. Science is crazy. We feel like what's the name? You know, Rick and Morty kind of crap, right? Okay. And let's get back to this. So yeah, answer Jushin's question, temperature is all in Kelvin. We are not worrying about systems where that inequality is not followed. Our temperature is well behaved, but if you want, you can go and read about negative temperatures. So let's get back to this. Where was I? Yeah, I was making some other interesting comment, which is, so this Clausius inequality is an inequality, right? It's not an equality. And it has existed that way for 200 years until 1997. Then something happened. Does anyone know who this is? Does anyone know who is Chris Jarzynski? Have you heard the name? No? I'm going to hide under a table. That's terrible. Huh? He's a what? Yes, he's a professor here. He teaches 481 every once in a while. Chris Jarzynski is someone who wrote a paper, and you can look up Jarzynski's relation on Wikipedia, which showed that if you take the exponential of both of these and then average over all paths, it becomes an equality. And this is considered to be the most important development in thermodynamics over the last 300 years. And he's a professor here, which is super cool. And 2 years ago, when Donna Strickland was given the Nobel Prize, in her Nobel Prize citation, you will see Chris's name is mentioned as to how experiments made it possible to experimentally verify Jarzynski's relation. So which is just to show that our department, we have a great history and also future in doing good thermodynamics. So you can read up about Jarzynski's relation. It's everywhere. It's a paper he wrote in 1997 when he was in Los Alamos. And since then, this relation has become very powerful to study things like protein folding and all. Because as I mentioned, if you want to study what is the free energy difference between a folded protein and an unfolded protein, you have to do the process very reversibly, right? Very, very slowly. If you don't do it slowly, then the entropy change, and if you don't do it slowly and you calculated the heat given to the system, then the entropy change that you're calculated is going to be an inequality. You don't know what it is. But Chris's relation, which we are not going to study here, Jarzynski's relation rather, shows that actually you can do an equality even for irreversible processes, which is incredible. So today I have told you 2 things which you can go and read as advanced material if you're interested. One is about Jarzynski's relation, the other is about negative temperature. I'm definitely not going to ask you about either of these in any homework or exam, but they are super cool. Super cool there's a pun there, right? They're so cold that they become hot. Okay, but let's get back to Clausius. The S system is more than equal to delta Q divided by T. Should I write delta Q reversible here? It would be true, there would be nothing wrong in it, right? But if I do delta Q reversible, then it becomes an equality, right? So this is reversible or irreversible, any process, and this gives you a bound on the entropy change in the system. And as a direct consequence, DS isolated system more than equal to 0 when spontaneous change occurs. If the system is isolated. Any questions about Clausius inequality? Okay, so let's calculate the entropy change of the system and of the surrounding for some practical situations. So we will do a little bit of that, and then we will gradually move into free energies, which are wonderful because you don't have to worry about the surrounding all the time. But unless you are doing free energies, which we haven't talked about yet, you always have to calculate surroundings entropy change also. And remember when we were doing that example of ideal gas expansion, and we calculated the entropy change, we did it only for the gas. As per that, it seemed like it was a spontaneous process because the entropy change was positive. But today we will show that actually it's not spontaneous, it's a reversible process if we actually calculate the entropy change of the surrounding also. So in order to do this, we have to think about the entropy change of surrounding a bit carefully. So we know in general that ds is equal to delta q and I'm writing small q, big Q, there is no difference, it's the same. ds is equal to delta q reversible by temperature, right? So I could use this. Let me put the reversible in superscript because I want to write this in the subscript over here. So we can say, we can apply this equation to the surrounding, right? This is a kind of a different way of thinking. We are not thinking about the system at all right now. We are thinking only about the surrounding. Delta Q reversible surrounding divided by temperature. If you were thinking of the surrounding as the system itself, right? You're changing your frame of reference. However, surrounding is a bit special than the system. The surrounding is something which is either constant volume or constant pressure. In chemistry, we typically, these are the two situations that we care about, right? So surroundings are either, it's not always true. You could imagine a situation where this is not true, but for almost all practical situations, either we will have a constant pressure experiment going on where there is no lid on top, or a constant pressure experiment going on where the volume is trapped. Constant volume experiment going on where the volume is fixed, or a constant pressure going on where the volume can change, but the pressure is the same as atmospheric pressure. So surroundings are either constant pressure or constant volume. Given this, we can do some, let's see, what's our equation number? Let's call it equation number 5. Given this, we can do something special with equation 5. We can say that therefore delta Q surrounding, and I want to emphasize here, reversible or irreversible, either one of these two, irrespective of whether it is reversible or irreversible, at constant pressure can be written down as dH surrounding. Is everyone happy with this? We have seen this for system, right? We are just changing our viewpoint and looking at the surrounding. And delta Q surrounding, reversible or irreversible at constant volume, can similarly be written down as, so notice we have taken this delta and replaced it with a d. We have taken the path function and made it a state function. What should I write over here at constant v? du, right? Change in internal energy. What does this tell us? This tells us that if you're willing to assume that your surrounding is either constant pressure or constant volume, the change in Q in the surrounding is actually change in state function. And if we have a change in state function, do we need to worry about reversible or irreversible over here? We don't. We don't even have to worry about the path. It becomes way simpler. Therefore, delta Q surrounding irreversible or reversible is equal to simply a delta Q surrounding. We don't need to care about. It's almost an abstract thing that I'm writing about here. But the point is, it can be very well behaved if it's a constant volume or a constant pressure process. So let's put this in action, and this will become clearer. Let's look at let's calculate it. It was probably just a bit confusing. Let's calculate it for a practical example, and it will take less than 5 minutes. We'll finish. So we are thinking about isothermal expansion of perfect gas from volume VI to VF. And let's calculate delta S total for this one, which is delta S system plus delta S surrounding. So we calculated delta S system a few classes ago. Anyone remembers what was the expression? We showed, if you look back in your notes, you will find that this was plus. Did anyone find it? It was a log. Remember, it almost reminded us of Boltzmann formula. Instead of log W, you had log volume. So it was NR ln VF by VI, which made us think that, oh, the entropy increases. It must be a spontaneous process. We did not calculate this one, right? So let's try to calculate this one. So I'm not doing this today again because we did it a few classes ago. Please go and look it up. I forget the exact class, but if you look on the notes, you should be able to find it. Let's calculate delta S surrounding. So for delta S surrounding, we have to note that delta Q surrounding must be equal to minus delta Q system, right? Because total delta Q has to be equal to 0. If the system lost some heat, the surrounding gained it. If the system gained some heat, the surrounding lost it. So these two have to sum up to 0. And again, if you go back to how we showed this, in order to do this, basically it involved showing that this thing is nRT ln VF by VI. Makes sense, right? Because we are talking about entropy. So if the entropy is what the relation between entropy and reversible heat is just divided by temperature, right? So this is nothing but the entropy over here multiplied by a temperature. Okay, I'm rushing through this. Next time I will resume from this point. So, but let's go through it once, and then I will pick up from over here next time. So therefore delta Q's, so this is Q surrounding, this is integrated heat. It has a minus sign. Does it make sense? If you look at the signs, it does. So now we can calculate delta S surrounding. What is delta S surrounding? That is Q surrounding divided by temperature. And why do I not have to care about whether this is reversible or irreversible? Due to this argument over here, right? Because the environment was either a constant pressure or a constant volume process. So I don't have to worry what happened to the environment or the surrounding. So this is going to be minus NR ln VF by VI. So if I take equation 7 and put it in 6, what do I get for delta S total? 0. This one was plus NR ln VF by VI. This one is minus NR ln VF by VI. So the sum total is 0. What does this tell us about isothermal expansion of perfect gas from volume VI to VF? Is it a spontaneous process? Is it a reversible process? Is it an irreversible process? Go ahead. Which one? Huh? It's reversible. Delta S is 0. Delta S is of the total thing is 0. And that is an interesting conclusion. If you have an ideal gas undergoing isothermal expansion, either of these is a reversible process. Therefore, either of these is a spontaneous process. So the whole thing is reversible. Okay. So I want you to go back and look at these two things from previous notes. And if it is still not clear, next time I will go through this argument again. Otherwise, next time I'm going to look at this same expansion, but occurring into vacuum. If the same expansion was occurring into vacuum, we will calculate the delta S total, and we will find that in that case, it is an irreversible process. And if this argument is confusing, please tell me, send me a DM, and I will go through it in detail next time. Otherwise, I will just go through the vacuum part.